So again, continuing chapter 11 notes, chapter 12 notes. This is, chapter 12 is focused on solid structure. There used to be a much more emphasis on solid structure. Now the AP test has decided you don't need to know as much about it. So you're going to see some extra stuff I put in here, and I'll tell you what you need to know, what you don't need to know. So metals and ionic compounds are typical crystal structures, and sometimes we're going to use the term crystal to signify solid structure. So these spheres are going to be considered an atom. So if I have a piece of zinc, okay, how do these atoms essentially orient themselves to each other? And so this first picture is what we call a simple cubic. Okay. Then next two pictures, the one on the left is called a bodied center cubic. And the one on the right is called a face-centered cubic. Bodied center cubic, you have essentially an atom in the middle, and then you have an atom on each end of a cube. Do realize that a lot of books and other resources color in that middle one may be different to show you perspective, but it could also be with an ionic compound. You could have a cation and then anion surrounding it, or vice versa. Face-centered cubic means that each one of the faces of the cube essentially has an atom. So I want you to think of a die, okay, as you throw dice in a game. Okay, if you think of the number 5 on that die, and you kind of have 5 circles, okay, and you have one circle in the middle, that's essentially how you should picture a face-centered cubic. So again, atom on each side, and then you have 4 essentially touching it or understanding its relationship. The last one is this one, and it doesn't do a very good job, especially when it's in black and white. What it essentially is a layering system, so that if we picture these atoms as being spheres, you're going to have little gaps. Okay, so these are little gaps that you see here that you could see through. What it does is, this is called hexagonal. I'll write it down. Hexagonal closed pact. And its abbreviation is HCP. Up here, face-centered cubic is FCC. The bodied centered cubic is BCC. And simple cubic, I think, is just SC, I think. But hexagonal closed pact, what happens is the layers go back and forth, so that you essentially fill in these gaps on each individual layer. Again, not a huge big deal, but it is the picture that you're seeing there. So if we are talking about these solid structures, we usually classify them in what we call a unit cell. So what the bad thing about those previous pictures is the spheres are essentially they're touching each other as close as they possibly can get. But a unit cell is essentially, what you're doing is cutting them into cubes. So the unit cell is the lowest repeating pattern over and over again. So this is a simple cubic, this is a face-centered cubic, this is a bodied centered cubic. And then down here, they're kind of showing you a hexagonal closed pact. Okay. So this next page that I gave you kind of shows you a couple different varieties of it. So here I like this the second picture, because it's kind of showing you how would I cut that essentially into a cube. So down here is more of the understanding of, okay, easiest one to understand is probably the body-centered cubic. So I have a whole atom in the middle, and then on each one of the corners, I essentially have 1/8 of an atom. So you could actually look at each one of these and count what we call how many atoms you have per unit. Again, it's not going to be a big focus for us, but if you would turn to the next page, kind of want to give you at least a little understanding of what these terms mean. So again, unit cell is the smallest repeating unit, and you can then break it down into those cubes. Well, if you have them in those cubes, you have something called a coordination number. And coordination number is the number of atoms surrounding an atom or ion in the crystal structure. Okay. higher the coordination number you have, the closer the atoms are to each other. And this is kind of important for solid structure. And again, not a huge emphasis, but a lot of universities and other academia is looking at material science. Material science is trying to figure out, can we get atoms closer together? They could then have different properties associated with it. So when we look at the types of crystal structures, you can base it on its coordination number. So simple cubic, you just have, if you cut them all at each corner, you got an eighth of it, you got a total of 1 atom per unit. Face-centered cubic, then you have a total of 4 atoms per unit because you have, again, a half on each of the faces. So your coordination number is going up. So what you will see is face-centered cubic and hexagonal closed packed have the highest coordination number. That means that they could get the closest atoms and you have a different property base. If you have your Flynn periodic table and you flip it to the side that has this particular key, you will see down here it will have what they call the crystal type. So you could see for even over here on the right, cubic, face-centered, hexagonal, and there's some other ones out there that we just don't cover. Manganese bodied centered cubic, chromium, hexagonal, so on and so forth. So it is inherent to the substance what particular crystal structure it has. Again, there used to be some math associated with it. I keep the formulas in there, but we just do not focus on any of that anymore. Instead, what we look at is kind of the different kinds of crystals that we have in chemistry. So ionic crystals are going to depend upon their size of ions or their charge, okay? So there are 2 things that ionic crystals are influenced by. And again, when we talk about these solid structures, we are looking at, again, their bonds within them are going to influence how a bunch of those crystals behave or interact. So ionic crystals are going to depend upon what we call the lattice energy, okay? The more stable the compound is going to be, the higher the lattice energy is. So of course, as we talked about with Coulomb's law back a couple chapters ago, forces increase as charge increase, okay? So if I have an Fe2 versus an Fe3, I have a difference in force if I have an iron 2 chloride crystal versus an iron 3 chloride crystal. Forces also increase as ionic size decreases. If I have Fe with chlorine versus Fe with iodine, I have a difference there because of the distance. So the force that we're talking about here is what we call the electrostatic attraction, okay, between those ions. So we have our friend Coulomb's law, okay? So ionic crystals are going to be influenced by, again, what we talked about before. And Coulomb's law shows up quite a few times throughout this semester and even into next semester. So with the ionic crystals, they have particular properties that lend themselves to some lab data that we can maybe look at and some other things describing them. So ionic crystals are usually hard crystals, meaning you can't crush them up. They have high melting points, and again, melting point is MP. They are poor conductors unless what we call molten or aqueous. So molten, again, is somewhat melted. It allows the electrons to move about because in an ionic crystal, because you have a cation and an anion, those electrons have been transferred. They're kind of locked into place. So because of that, they don't conduct very well, having to do with that. And another one you could write here is they are brittle, meaning because they're such a hard crystal, you can't crush them, so they will flake off pretty easily.